Welcome, everyone. Today, we're diving into the invisible world above us, the atmosphere, and the complex chemistry happening within it. Understanding this atmospheric chemistry is vital because it directly impacts the air we breathe and the health of our planet. Air pollution isn't simple. It's a dynamic mix of numerous chemicals reacting in the air, forming aerosols, and even interacting within clouds. Figuring this all out requires some seriously smart tools and techniques. Over the years, scientists have gotten much better at actually measuring what's in the air. Techniques like high-resolution mass spectrometry let us identify a huge range of organic compounds, even fleeting ones we couldn't easily spot before. This gives us an incredibly detailed picture of the air's chemical makeup. Then there's remote sensing. Using ground-based tools like LiDAR or satellite instruments like Tropomi, we can monitor key pollutants. Think nitrogen dioxide, sulfur dioxide, ozone, and formaldehyde over vast areas. This is crucial for tracking where pollution comes from, how it travels, and whether air quality rules are working. Plus, new, cheaper sensors are popping up, creating networks that give us fine-grained data, especially useful in complex city environments. By combining data from labs, field studies, monitoring stations, and satellites, we get a much more complete understanding. Alongside these measurement breakthroughs, the computer models used to simulate atmospheric chemistry have also evolved dramatically. These chemical transport models, or CTMs, now include thousands of reactions involving hundreds of chemical species. They simulate everything from emissions to transport, chemical changes, and eventual deposition. Modelers are focusing on several key areas. One is multiphase chemistry, the reactions happening inside or on tiny atmospheric particles and cloud droplets, which significantly affect air composition. Another huge area is secondary organic aerosol, or SOA. This stuff makes up a big chunk of particulate matter and forms when organic compounds react in the air. Models are constantly being improved to capture this complex process better. We're also seeing models run at much higher resolutions, down to the kilometer scale, which is essential for understanding air quality differences within cities or near highways. Techniques like data assimilation are used to merge model predictions with real-world observations, making forecasts more accurate. And increasingly, machine learning is helping to speed up calculations and find patterns in the massive datasets generated. But the real magic happens when we bring measurements and models together. Detailed measurements provide the real-world data needed to build and test the models. In return, models help us make sense of complex measurements, point out where our knowledge is lacking, and predict what might happen under different scenarios, like changes in emissions or climate. Of course, challenges remain. Fully understanding how organic aerosols form and behave, figuring out chemistry in vastly different environments, from clean forests to polluted cities, and improving our knowledge of emission sources are all active research areas. Continued innovation in both how we measure the atmosphere and how we model it is absolutely essential if we want to effectively manage air quality and protect our health and environment. Thanks for tuning in.